Hi Omar, how you going, mate?
I'm doing great. Thank you.
Awesome. It's great to have you live with us today.
Yep. Thanks for hosting me.
No, it's awesome. It's a great presentation. I love that one. We have had quite a few questions come through from the audience there. The first ones are around licensing. So there's a couple relating to licensing. So I'll give you the first one there. What licenses are required to use machine learning?
That's a great question. And I get this question a lot, by the way. So think of machine learning as a horizontal capability that we have in different products in ArcGIS. So for example, if you want to use the deep learning capabilities with imagery, like similar to what you guys have just seen, you're going to need image analyst extension with Pro 2.5 or 2.6 if you want to do this work locally, right? If you want to scale this work, use distributed raster analytics, your enterprise server 10.7 plus, like 10.7, 10.8 with image server. Now that's regarding deep learning with imagery. Now let's say you want to do this workflow that you've just seen, imagery, but with point cloud. You don't need image analyst for it. You just need 3D analyst extension to handle the 3D data and do the kind of analytics needed with 3D. But for the deep learning piece itself, you can do it either locally or in an ArcGIS online notebook, right? And finally, for the machine learning tools in Pro, like predictions using geographically weighted regression or the other tools in clustering, most of these could be done in Pro Basic, but some of them will need the spatial analyst extension. So the answer is simply think of the needed workflow, and based on this, you're going to have different kinds of licenses that you're going to need.
Okay, thank you. Great answer. The second one that's coming through there in regards to licensing, do we need separate, and you obviously touched on that there, but do we need separate licenses for the deep learning model, or is this inbuilt within ArcGIS Pro?
Here's the thing. If you want to train the model, you don't need any license, right? You can do this through the Python API, right? You can do it in an ArcGIS notebooks, in Pro 2.5, etc. Now, if you use the model, consume the model, you don't need a license for the model itself. Like, by the way, we have some of the publicly available pre-trained models that you can download today from the Living Atlas. I absolutely encourage you to go there and have a look. Go to the Living Atlas, search for deep learning. You're going to find 3 models there, and we're going to keep adding. But here's the thing. If you want to do using the model, if you're against imagery, overhead imagery, you're going to need image analyst extension. If you want to do this in server mode, like in a Jupyter notebook, for example, executing against server, you're going to need image server. So either image analyst or image server is going to do the job. If you want to do deep learning with vector, you don't need a specific license for that. If you want to do it with point cloud, you don't need a specific license for that.
Okay, thank you. The next one starts off with a big, great presentation, Omar, and then it leads on to the question being, how do you scale the models on the end-to-end AI lifecycle?
That's a very good question, because sometimes we deal with customers who want to run deep learning models across entire cities, states, or even a country in a couple of minutes or like hours instead of days and weeks, right? So there are 2 pieces for that. One piece is related to the power of GPUs that you're using. The other piece is related to how you parallelize the inference process. So for the first one, I highly recommend good, powerful GPUs. So go for V100, for example, right?
Yeah.
Start at least with an NVIDIA RTX 2080, right? Go to a V100, have a more powerful GPU, right? So that's one piece. The other piece is try to parallelize the inference by using distributed raster analytics, using multiple image servers or multiple raster analytics servers. So as you guys know, we have something called distributed raster analytics, one of which is deep learning. So we have been doing this, for example, to run deep learning models to extract building footprints across a major city in the US. This locally took us almost 4.5 hours. Doing it with 4 image servers took us almost 20 minutes. You can save using like 4 servers. So I would highly recommend good, powerful GPU. The second thing is use distributed raster analytics, multiple image servers with enterprise to scale the inference process. These are usually 2 recommendations to speed up the inference. Now, for speeding up the training, you can the better GPU, the greater. And eventually soon, we're going to allow training on multiple GPUs on the same machine. So that was a long answer, but I hope this answered your question.
No. That was a great answer. I guess I wanted to add a little bit onto that too. So here in Australia, a lot of the clients that I work with in particular, they use the AWS or Microsoft Azure clouds. Do you leverage clouds like that to distribute the image service?
Oh, absolutely, all the time. And thank you for reminding me. Actually, with most of these workflows, we either deploy in Azure or Amazon most of the time. I mean, technically, you can do it on premise, but we highly recommend the cloud for that because you can use the virtual machines there. So, for example, on Azure, we use the virtual data science machine, right? The data science virtual machine, which has a type of it called the deep learning virtual machine that comes with GPUs, right? You can choose whatever GPUs you want. You can scale this up and down elastically. We are doing the same thing with Amazon. So yeah, absolutely is a recommendation if you want to scale these workflows.
Great. That's awesome to hear. I'm sure we'll get probably a few questions about that one, I would think, following up. Okay, so on to our next one. And this is in regards to the bit there where you talked about building a training data set. And I think the question sort of centers around how long it might take to build a deep learning training data set for, say, locating solar panels on residential rooftops or counting solar panels on residential rooftops.
That's a good example. I would break down the question to how much training data do we need, because time is a factor of quantity, right? So how much training data do we generally need to train deep learning models, and specifically for solar panels? The answer depends on a couple of things. I would say the more the feature or the object you want to detect is obvious, the less training data in general you need. The less diversified the flavors or the versions of this object, the less training data you need. Let's say you want to detect solar panels, as you just mentioned. I mean, solar panels might have some variation of solar panels, right? So what different types of solar panels, maybe 5, 6, 10? It's not like, for example, cars where you have like different versions, and trucks and small cars, and or trees, you have tons of species and stuff like that. So let's say you're interested in detecting 3 or 4 major types of solar panels. In that case, it's less. The object itself, the more high the imagery you have, the less training data. So I would start with a couple of thousand, like 3,000 training examples, and use the image augmentation technique, which we have in the Python, to generate even wider variety of these. So the image augmentation takes your input training data, it applies different distortion techniques to it and rotations, and helps you have like 10,000, 8,000 instead of 3,000. So if you want to do 2 to 3,000, you can crowdsource this. You can have a team of 5 or 6 working in parallel using the labeling app in Enterprise or on ArcGIS Online to label data, and you can absolutely do this in a couple of days, right? So this is in regard to solar panels. Another example, let's say building footprints. In an area that has different types of buildings, you might need like 10,000 training examples. So you might need more days. The amount, which relates to how obvious the feature is and the resolution of the data, and then think of the time. In solar panels, I think it might need like a couple of days to generate good quality data as a starting point.
Okay, great. That's amazing, and that's good to hear that might not be a really time-consuming task to undertake there. You mentioned collating large amounts of imagery, and it's sort of based on the business need and what you're trying to analyze. What is some of your best practice advice for collating, say, really large deep learning training data sets?
So I have a couple of advices. First, try to spend some good time to get quality training data, because if you don't have good training data, you're not going to be able to train models that generate good accuracy. So try to have diversified examples, right? So let's say you want to detect a specific object, right? If you want to detect, for example, try to get different examples of each type of solar panels. If you want to detect tree species, try to be as diversified as possible. So that's one thing. The other thing, geographies. Don't just take data from a specific different cities, different geographies, different regions, right? Try to take data in different sensors if possible, right? I mean, if you're going to run these models across different imagery, try to take training data from this. So that's the first advice regarding training data, right? The second one is regarding hardware. I would generally recommend doing this in the cloud versus on-premise because it's easier to spin up powerful machines, right? Depending on the need, you can spin up different versions of virtual machines. You can choose different GPUs and stuff like that. If you're going to do this locally, try to get a powerful GPU and a powerful beefy machine to do this kind of processing, right? Like the V100, for example, is a good GPU and stuff like that. The third thing is try to experiment with different types of neural networks because there is no one size fits all. It's optimizing the neural network to produce the best results, right? So if you want to detect objects, for example, try different backbones. We support different neural network bones right now. We have the ResNet with different like depth, right? We have almost 3 versions supported, right? So play with different neural parameters easily without trying code today in Pro. If you have Pro 2.5 or 2.6 with Image Analyst, you can do this today. Try to play with different neural networks, optimize different parameters, see which is better, because deep learning or machine learning in general is a very iterative process. And keep doing this, keep iterating until you have good results. If you don't, get back to step 1, collect more training data, try different networks, keep pushing, keep looping until you have good results. Don't give up, because it's a very iterative process. These would be my general advices if you want to pursue deep learning with imagery.
Oh, awesome. That's some great advice there. Invaluable advice, to be honest. That's really amazing stuff that's going to help our clients a lot, I know. There's probably enough time for just one more question there, and it's relating to determining tree species from 3D point clouds. That's one that's come through, and I think the question's centered around, are you able to share the percentage of species that might be successfully identified in this type of analysis?
So I don't have the specific species on top of my mind, but I recall that out of 5 or 6 species, we got almost 4 of them with like 75% accuracy. But I think this answer is a very relative answer, right? Because it highly depends on the species that you want to detect or the user, not what we have done, and the amount of training data that you have available. If you go to the Living Atlas today, you're going to have a point-CNN model that can detect trees from point cloud. We don't claim to be, but it's a good starting point. So I would start from there. Try this model first, see the kind of results it's generating, and then keep fine-tuning it with more data. Because the Python API gives you the ability to train or retrain models that are pre-trained with your new data. And if you're not getting good results, keep adding more good data and try to optimize the neural network. So in our case, it was like about 75% accuracy for like 4 of the species out of 6, I think. And in your case, I would try it out and keep adding more training data if needed to optimize.
Okay, well, thank you. So it looks like we are just about out of time for those additional questions there that have come through for you, Omar. But what we're going to do, we'll collate those and we'll get those through to you, and we'll get back to you on those and get back to the audience. But thanks again for your time, Omar. We really appreciate that advice, and thank you.
Thank you so much again for inviting me, and have a great day.